This tutorial implements 2D diffusion equation with a source, and in this case what we have is a metal sheet with a hole in it. This hole, we can put this hole anywhere for the sake of this experiment, but what's given to us is that the top, bottom, and left edges are at 0 degrees Celsius, whereas the right edge is insulated. So this would be the Neumann boundary condition, and these other three will be the Differential boundary conditions. And we are also given that initially this whole plate is at 0 degrees Celsius, but at some time at t is equal to 0, we bring a source at 7,3 coordinate. So this is a 10 by 10 meters sheet. So at 7,3 we bring a source and we leave it there for 5 seconds and see how the temperature of this sheet evolves over time. So the 2D differential equation for the diffusion process is we have the first derivative of time and then 2 second derivative, one with respect to x-axis, one with respect to y-axis. And the thermal conductivity in this case will be a function of space as well, because as it's given that this hole is plugged with a material which has a very low thermal conductivity. So we have to take that into consideration as we are implementing. So in this case, when we discretize the equation, we have to discretize k as well. So we have k as a function of space. And then when we rearrange this equation, we get similar kind of update that we got for the 1D case, but in this case we also have y dependence. So the second order derivative will have a 4t term with the other 4 nodes, the neighboring nodes, added to it, and then we have the source term as well in there. And since dx is equal to dy, we'll be only using dx. So after a little bit rearranging, you can see that the new value of temperature at ij is equal to the old value of temperature at ij plus some terms, so plus the diffusion term plus the source term. And this is what we will be implementing in the 2D case. The auxiliary conditions are given to us, where the initial condition is set to 0 everywhere, and the boundary conditions are Dirichlet at the left, top, and bottom, and then on the right edge we have the Neumann boundary condition. And the source is given to us. It's equal to 100 for 0 to 5 seconds and 0 after that. So these are the things that we'll be using. So in order to implement, we'll just take our diffusion 1D source and we'll make a copy of this as 2D source, and we'll just edit this one. So first of all, note that this top part will have some constant times tx plus some constant times tyy. So that's the part that will change, and we'll also have another constant b times the q, the source function. So this is what we need to take into consideration in this case. So rho is equal to 1, specific heat is equal to 1, but k we need to define later because it's not just 1 here, it's a function of space. We won't need a anymore because it's not going to be a constant value as before anymore. The Lx is equal to 10 and Ly is equal to 10 as well. And in this case, what we can do is we can set the Ny values equal to 51 as well. So in this case, of course, we can calculate dy is equal to Ly times Ny plus divided by Ny minus 1, but it will have exactly the same value as we have assumed in our problem, that we want dx and dy to be the same. So dy should be equal to dx. And if it's not equal, then you can always go back here and have the two terms separated. You can have dy term as a separate piece there. Now we again have our CFL condition, and in this case I'm going to reduce it a little bit so that we can have a little bit smaller time interval. And now the temperature will have two dimensions. So along the in MATLAB, what seems to be x dimension is actually y dimension, because x dimension is along this way, but these are columns. So columns are the second argument. So we'll put ny here. So this gives us the temperature matrix. And similarly, we can also create our y-axis information here, how our y-axis values change. These will be ly, ny, and then this is our y-axis distance. And using these two, we can create our mesh for plotting purposes. Now again, the initial condition, what we have is Tn. Now we have two-dimensional matrix. All of the values are 0 at time is equal to 0. Now here is where we need to define the parameter k. So here we have to define the k thermal conductivity, which has exactly the same size as our temperature scalar field, but now has values of 1. So 1's size ny and nx. And as you can see, we have to create it this way because part of the sheet has very low thermal conductivity. And let's say we put that hole somewhere here, let's say 20 to 25 and 30 to 35. And that's where we are saying that the thermal conductivity is very low, let's say 0.001. So if we run this code up to this point, we can actually see, we can do image sc, which you have known before the command, and you can see that this is a little hole that we have created. So our source is somewhere here, and then we have a little hole over there with very low thermal conductivity in the sheet. Okay, so now the next step is we create the loop. Again, we are running it for 500 time steps. We save the current location, and then this is that we needs to be updated based on this equation. So here we will need to replace the constant term. We will need to add the two neighbors and also update the source part. Going back here, we will add the constant. Now again, it's the thermal conductivity at J and I divided by rho divided by Cp. And as you can see, it has J index as well, so we need to create a second part of the loop, which is J going from 2 to ny minus 1, and then also we have to end this loop after this part. So now we have J and I. So all of these locations where we are updating temperature should become J comma I, J comma I, J comma I plus 1, J comma I, J comma I minus 1 divided by dx times dx. So in order to just have a little bit more, to divide this into two lines, we can put 3 dots and take the rest of the command to the next line. Now this is the part where we have to also include the other two neighbors, so J plus 1 neighbor and J minus 1 neighbor. So we'll take this to the next line as well and copy this, so or we just TC, and this is J plus 1 comma I, and similarly on this side we'll have another plus TC j minus 1 comma I. So we have all of our terms here now. So following on the same line, now we have to also update the source location. So sy is, we know that along the y-axis it's 3 units, round 3 comma 3 times ny divided by ly. So this is the y location of the, and we want to put this in the temperature field at that particular index location. We are adding the value of the source, and so that sort of completes that part. And the boundary conditions, we have new boundary conditions, of course, so let's update those. So Tn on the top, so top is the or let's start with the bottom. Bottom is the first row and all the columns, that's 0. Then the top one would be the last row, all columns is equal to 0. Now the left edge is Tn all the rows but the first column is equal to 0, and then the last edge will be the all the rows but the last edge. But this one, for the right side, we have a Neumann boundary condition, so this will be Tn at end minus 1. So just the column before that has to be assigned. So make sure you understand how this last condition comes through, so is derived. Okay, so now we just have to plot it. So instead of plot command, we will use mesh command, x comma y comma Tn. So this is a 3-dimensional plot, and we will put the axis limits here. Axis, we can put the limits for each one of the axes. So the first axis goes from 0 to Lx, the second goes from L0 to Ly, and the third we can take from 0 to maybe 50 degrees Celsius for now. We don't need the labels anymore. We set up the title, and that completes the code. So now we can test it by running it, and let's see. So it looks like it is blowing up. So what we can do is go back and look at our code. So looks like here this one is supposed to be 4. I made a mistake there, and then looks like this is supposed to be I. That was a mistake that we need to make. Now let's run this code again. It looks like now it's running fine. The source is very small, that's why we don't see much action happening. So let's increase the amount of source, maybe to 1000, and then we will only let this source run for maybe 3 seconds to get the feel of it. So there you go. So now you can see how the source is going to run for about 3 seconds, and then it's going to stop, and then it starts to go down. And this side is insulated, so you can see how the effect of that really low thermal conductivity material shows up there. It's not allowing much of the energy to move through, so the temperature here is cooler, and you get this profile of the temperature because of that. So hopefully this will give you an idea how you can implement a 2-dimensional diffusion equation. The same idea will apply if the other components, say density or the specific heat, were also function of space. Then you would have all of these defined as arrays. So you can define arrays here for specific heat and density as well. So this concludes the tutorial.